Pretend the world doesn't exist. Okay, here's where we are in terms of lecture material. So we'll do the end of 15 and some portion or all of 16, 17 super quick, so that usually spills in. I haven't done it yet. I will give you bullet points, and I'll put them right here in the beginning of Assembler 1. I'm going to give you bullet points, which are things I want you to know for the exam about Assembler. So, and what would they be? They would be things like, well, for example, I'm going to tell you what spilling is today. What's spilling? Or, you know, how do you access the parameters of a procedure? Right? Which, you know, hopefully you would give me something that wouldn't be embarrassing for that. You know, what delineates a stack frame? I don't know. I'll tell you fairly precisely what I want you to know, and that way you can just study that. It's funny, when I took a course in college called Psychology of Music. Did I take it as an easy A? Yes, I did. And to fill out those distributional requirements like you always do, right? I assume you find the easiest, global civilization class to get your A, so you don't have to spend any time. Well, that was me. And you know, people do that with us too, right? Finite math, right? That's the one they take. But anyway, I was taking psychomusic, and the guy, I've never seen someone do this before. He gave us a list of 40 questions with their answers, and he said, the midterm will come from these questions. I'm like, this is the easiest class in the world. Like, how could I not get an A? But people didn't. I mean, how did you not know? 40 questions? I'll give it to you verbatim if you want. Close to it. Anyway, that's what I'll do for you with assemblies. I'll give you precise, probably 5 to 10 takeaways from assembly code. And that way you don't have to be like, oh God, I have to convert this assembly code, because that's what I used to do, is make you convert C to assembly code or read a stack. And I'm not going to do that to you. So, all right. So where we were, what did we learn? We learned the general architecture of our fictitious machine, right? Eight registers, 5 of them general purpose, R0 through R5, 3 special ones, program counter, stack pointer, frame pointer. Frame pointer points to the bottom of your frame, the lowest address of your stack frame. The stack pointer points to the first top unused element on your stack frame. And then when do you mess with the stack pointer? Well, when you allocate local variables, you call push, and that'll give you room on your stack. And then when you access those variables, you're going to access them from the frame pointer, because the stack pointer can move. Okay? Where else do you use the stack pointer? When you're doing procedure parameters, you push them onto the stack in reverse order before you make your JSR call to run the procedure. And then when you call JSR, then contextual information about where you are gets stored on the stack. So your program counter plus 4, which is basically the next instruction you want to run when the procedure's over, that gets stored in the stack, plus your frame pointer gets stored in the stack, and then the frame pointer gets moved, and now you have a new fresh stack frame. And when you call return, it pops those things off the stack, and then boom, your old stack frame is restored, and you are running the code right after what you were running before you made the procedure call. Okay, and those are all kind of takeaways. I'll codify them. Those are kind of the takeaways you want to get, regardless of whether we're running my assembler or any other assembly. These things are all the same. You still have to be able to run procedures. Okay, we're going to talk about spilling now. So spilling is when you have to store a value temporarily on the stack because you basically need to free up some register room. Okay, so again, this happens with all assemblers, all compilers. Let me give you a motivating example. Okay, before I give you the motivating example, let's just talk about when you make a procedure call. Okay, first off, what happens to the register R0? You make a procedure call. What's going to happen to R0 when the procedure call returns? Yeah, it stores the return value. If there's a return value, that's where it's stored. So you know register 0, whatever value it had when you called that procedure call, is going to be gone because it's returning R0. What about the others? This is actually a decision you have to make. And the decision that we make on my machine is that when I make a procedure call, obviously R0 is going to get trashed when it's returned, and R1 might be trashed. So I can't make any guarantees about what R0 and R1 are when that procedure call returns. However, R2, 3, and 4, I'm going to guarantee that whatever values they had before I made the procedure call, they're going to have when the procedure call's over. Okay? That's as a compiler writer, that's going to be my decision that I make. Okay? So you can do a few things. You could store that value before you make the procedure call and then restore it afterwards. But what if the procedure never used the register? That would be wasteful. So instead what you're going to do is if you as a procedure are going to use register R2, R3, or R4, you need to store its value on the stack right after you allocate your local variables. Okay? And then right before you return, you're going to restore them from the stack. That's called spilling. Okay? It's called spilling the value of register. I don't know what it means. You got the value of the register there in a cup of water and you spill it on the stack. And then I guess you have to mop it up afterwards. Okay? So let's give an example. Okay. Actually, put this over here. Yeah, whatever. There we go. Okay. Let's just write some code. Let's start with main. Okay. First thing with main, we're going to call push4. So we can have I, right? So now I is in FP, right? And then we want to call the procedure A with the values 22 and 40, or 44 and 22, so we're going to push them onto the stack in reverse order. So move 22 into R0, and then store R0 onto the stack. All right, and then we're going to do the same thing with the value 44. And now we'll call JSR A. First thing we need to do is call pop 8. All right. Is get the arguments off the stack. And then we'll go ahead and store the return value into I. And then we return. Okay, so main's pretty easy. And again, since you all do this for a lab and I don't make you do it for an exam, you don't really care that you could do this or not. It'd be nice if you could, but life's only so short. So instead, I'll do it. And hopefully you can understand what I'm doing while I'm doing it. Ooh, I didn't. Hopefully you understand enough to know that I need that line there. Okay, now with A, okay, we had the same thing, right? We got to allocate room for K. Now if we look at this arithmetic statement, right, think how many registers do we need? Well, I can load I into a register and I can add 2 to it. So that's going to be register, if I add 2 to it, I got to put 2 in a register and do the add. So that I plus 2 has to use 2 registers. Okay. Similarly, J minus 5 has to use 2 registers. Well, if I'm going to hold one of their value while I calculate the other, that's 3 registers I need. I need R0, R1, and R2. Because of that, I've got to spill R2 onto the stack. So store R2 into SP minus minus. All right. Spill R2 because I need it. Okay. Now, we'll come back to that. Oh, that's this one. Often what I do with these arithmetic things is I'll turn them into a tree. Right? Makes sense. Right? So if I want to do this arithmetic expression, I can create this tree, and then when I execute the tree, what algorithm am I doing? There are 2 algorithms from the courses you have learned in your curriculum that allow you to process this tree correctly to get the correct arithmetic expression. Any thoughts? Guesses? DFS? DFS? Yeah, a specific kind of DFS.
In-order traversal?
Close.
Pre-order?
Post. Right? You can't do the times until you've done everything. So if you're going to print it, it's an in-order traversal. But when you're executing it, I've got to do this before I do that, and I got to do this before I do that. So it's a post-order DFS, right? So make the recursion first and then do your operation. There's another one. If this were a directed graph with the edges going up, topological sort. The one that we all forget from CS302. Yeah. But in doing that helps us with our writing our code, because now we can just do it, right? We can say, oh, let's also, while we're here, it's always good to label. So K is FP. Here you can look at the thing. Here we can go into complete multimedia mode. Look at that, 3 windows. Kind of. All right. K is FP. I is what? In a week, you've forgotten everything. FP plus 12. I know you were studying. Right? FP plus 4 is the old frame pointer. FP plus 8 is the old program counter. FP plus 12 is the first argument. FP plus 16 is the next argument. So J is FP plus 16. Okay. So I'm going to spill it, and now I'll go ahead and do it. So I can load I, right? So load FP plus 12, put it into register R0, move the value 2, put it into register R1, atom, R0, R0, R1, put it into R0. Okay, now we'll load J, FP plus 16, move, put it into R1, move -5, put that into R2, atom, y'all aren't finding my bugs, that'll be 1, that'll be 2, put that into R1, and now the final multiplication. So multiply R1, R2, no, R0, R1, and put the result back into R0. Whew, okay. And now I got to return K, so now and I got to store it, right? Store R0 into K. And now I got to return K, so I got to load R0. I'm sorry, load K, FP, put the result into R0, and return. And I'm done. Okay? And again, we don't optimize. We could optimize. We could delete those 2 lines and we'd be optimizing. But we don't. Our compilers don't optimize. Optimizers optimize. Okay. Do we want to see if it runs? Oh, yeah, Jamin.
Your last add should be a sub.
My last what?
Your last add instruction should be a sub.
Oh, yeah, I could. I put -5 and I added. I always like doing that. And the reason is that then I can take advantage of the commutative property and the associative property. And sometimes that makes my life easier. We'll actually see it here a little later in the class.
In that move instruction, it's a T2.
Oh, thank you. Thank you, Team Plank. All right. All right. Here, we'll see if it runs. There we go. Okay. Let's go to assembler 2. And the thing we just wrote, which was temp.txt. Ooh, nice, compiled. Okay, not much exciting here, right? So what are we going to do? We'll commentate, okay? We've allocated room for I on the stack. We're now pushing the 22 onto the stack. We're pushing the 44 onto the stack. We're going to make the JSR call, which now stores the program counter, stores the frame pointer, gives us a new stack frame. We now call push 4 to allocate the room for K, and now we spill. Right there was the spill. Doesn't matter that we spilled a 0 because that's what was in the register. We don't know who's calling us, so we got to spill it because we got to make sure that that value is the same when we return. Okay, so now what do? Load I, load 2, atom, load J, load -5, atom, multiply the result, Do we care? No, we're not going to double check this. Store it into K, load it from K into the register R0. We're done. Pop our arguments off the stack, grab the return value. Okay. Okay. We can show why this matters. I won't go through the JASM for this, but if we look at maybe I spill 2 dozen. Okay. Same A here. But what I've done is I've changed main. Okay, so I'm going to write some code. Okay, A is the exact same, but now main's a little different. And why is a little different? Well, since it's calling A once, and now it's got to store the return value because it has to add it to the result of the next call. So where is it going to store that return value? It's got to store it in R2, R3, or R4 because those registers' values won't change when A is run. That's why it's important that they don't change. So I've got to store, so I'm going to store it in R2. Since I'm modifying R2, I've got to spill it. Right? Even though I'm in main, main's nothing special, it's just a procedure. Okay? So if we did this, the first thing we do is we would store R2 onto SP minus minus, right? So spill R2 because you're using it. And now we do this the same thing. So now we'll move 20 into R0, store R0 onto the stack. Right, do the same thing with 10. Right, arguments in reverse order, call JSRA, pop 8, because we put that on the stack. And now we're going to move R0 to R2. Right, so that's we got our return value. Now we got to store it in a place where it's not going to get messed with when we call JSR again. Okay, so now I'll just do the same thing here. Only now I'm doing 30 and 40, so that'll be 40 and 30. JSR pop 8, and now I can do my final return value. I can say add R0 and R2, put the result in R0, store R0 into I, FP. Not quite done yet. We got to unspill. Right, so now I got to load SP. Did I do that before? I didn't unspill before, did I? I totally didn't unspill. We've got to unspill. So we've got to load plus plus SP into R2. Right? Because, remember, the stack pointer points to the first unused thing on the stack. So when we want to load from it, we're going to increment it first and then grab what it's pointing to. Okay, and so same thing down here, because we're spilling, we got to use it. Okay. I assume we don't need to see the JASM running on this one. It's pretty straightforward. I don't think it has much in terms of illustrative value for you. Aren't you glad I'm not making you write this on an exam? I'm glad I'm not grading it. You can give me feedback, though. When you're doing the final feedback for the class, maybe I'll try to remind you of this when that time comes. Right, after you tell me I'm a jerk and everything, then say whether or not you'd like a lab. Right? Would you like an assembly code lab? Or would you like a specific assembly code exam? Can't imagine the answer to any of those questions would ever be yes. But you never know. Sometimes people surprise me. I mean, I got rid of the lab because it was so hard to grade. Right? It was brutal for the TA to grade. So I stopped doing the lab. And then I would ask it on an exam. And so here we are. Okay, there's another time when you spill. So, okay, so one, you spill when you're going to use a register and you have to maintain that value of the register across the procedure call. The second time you spill is when you run out of registers. There are times when you might run out of registers. Now let me give you the example of that one. Okay, I mean, it follows a pattern, doesn't it? Right. So I gotta use, so when I do this, I gotta store the value in R2 when I do the, or well, actually here I gotta store the value in R2 when I do those two. Okay. And then here I gotta store it in R3 because I gotta be storing this one in R2. Right? And so eventually you'll run. So let me uh-oh. Is that it? Yes. So if you take that expression and build it into a tree, okay, this is what you get in the tree. So right, when I call A2, I got to store its value in R2 because I got to keep it when I'm calling A3. I can store that value in R0, but then when I add them, I got to store it in R2 while I'm doing this tree. Right, so this tree I got to use R3. So now if I store this value into R2, right, now I got to store it while I'm doing this tree. This is going to use R3 for this, R4 for this, and now I move up, right? Here, when I got to store it in R2, well, when I get to this point finally here, I've run out of registers. Right, so I've been able to do a lot. So when I do that, what do? Well, what I do is I'll go ahead and spill R2 onto the stack, and then I'll use R2 in here. And then when it comes time to do this final multiplication, I'll unspill R2. This is up to your compiler to do. Okay. I have the code. No one wants to read the code, right? I mean, the code is brutal. Where is it? .js. There it is. Right? But it starts off, so it is that kind of good to see, right? It starts off, you got to spill R2, R3, and R4 because I'm using them. Okay? And then I go ahead and do these, and then right after I calculate this value right here, okay? Right after I calculate it, that's when I go ahead and I spill it. Do I spill it? And yeah, so I spill it. So here's when I do the addition, to do that final addition, and then when I'm done, I spill that return value. It doesn't have to be an R2, it's just that the result of that addition has to be put on the stack. So that's put on the stack, and then after I do all this calculation, right, then right here, after I perform this addition, okay, then I go ahead and I unspill. Do the multiplication, I'm done. And then at the end, I got to unspill everything again. Okay. Again, we can go through the JASM. I don't think it's going to make anyone happy to do so. I do have screenshots in the lecture notes, which is very exciting. In the lecture notes, I will show you the highlights of JASM, right? Plus the code there and where the spilled stuff is. So in case you really want to go through it, you can. Can't imagine you would, so you won't. Okay, that's the end of that set of lecture notes. Except, Michael has a question?
You may have already said this,
yeah.
But if you don't unspill at the end, what happens exactly?
So it's a good question. So if I don't unspill at the end, then whoever I'm calling, whoever is calling me, that value of R2 will have changed on them. And so if they don't use it, okay, that's not a problem. But if they use it, now they've got now you got a bug in your code.
So essentially just a variable change then.
Yeah, just change of value. I mean, it's and those are. I mean, imagine debugging that. That's going to be a giant pain. That's like when you stomp on memory. Right. Those are really hard bugs to follow. Yeah, Daniel.
I have a question about how your stack is actually stored in memory.
Okay.
So does it kind of start at the top and work down to lower memory addresses?
So
limited space, right?
there is limited space. So in your executable, the way it works, and I'll get to this more in some subsequent lectures. The operating system and the hardware set it up so that you look like you have this big address space, 0 to 16Fs, right? And it looks, that's your memory, right? Now in reality, it's not your memory. The hardware does some magic, and the operating system sets it up. You'll learn about that magic in CS361, hopefully, okay? But it is set up so that if you have some of these addresses just don't exist, if you try to use an address, you'll get a sig fault. Now, so when it's setting up your address space in the beginning, there will be one region of memory, typically at the end, which is why I give these big numbers. Big thing, it's 8 megs. So it's big. It's 8 megs. That's your stack. And the stack pointer and the frame pointer start right at the end of it. Okay? And so now you use the memory by decrementing the stack pointer, right? And calling GSR and having the frame pointer bump up. If you did that more than 8 megs worth, you get a seg fault. So that's why infinite recursion gives you a seg fault and not any other mistakes. Because with infinite recursion, you run out of stack space and get a seg fault when you have an address that doesn't longer exist. Okay, so even though we manipulate this stack by decrementing stuff, we don't do anything to like grow the memory or ask the operating system for more memory. It's just a fixed region of memory that you use for your stack. I hope that answers your question.
Yeah.
Easily. Okay. Others. Let's click. All right. You get big fonts here. Oh, thank